This video is about absolute versus conditional convergence of series. For this video, all series will be regular infinite series. There will be no power series. You should know what it means for a series AN to converge versus diverge, but you don't need to know any specific series tests, although the following tests will be mentioned in examples: the p-series test, the geometric series test, and the alternating series tests. If you don't know these tests, however, you can just gloss over these parts. Our main focus is going to be to explore a series AN versus the series of the absolute value of AN. Let AN be a series. If some of the terms AN are negative, then taking absolute values will result in a larger sum, because instead of subtracting off the negative terms, we will be adding them instead. So the sum of the series will be less than or equal to the sum of the series of absolute values. This will mean that if the series of absolute values converges, in other words, this sum is finite, then the original sum of the series will be finite. In other words, if the series of absolute values converges, then the original series will converge. Now, I am glossing over one point, which is that it's not possible to have a series that diverges to negative infinity while having the series of absolute values be finite. That doesn't happen, because if the series diverges to negative infinity, then the series of absolute values will diverge to infinity. But given this assumption, we can see that if the series of absolute values converges, then the original series converges as well. And this will be very useful. Let's take a look at an example. Let AN be negative 1 to the n times 1 over n squared. The negative 1 to the n is an alternating factor. When n is even, negative 1 to the n is 1, whereas when n is odd, negative 1 to the n is negative 1. And so the terms of this series alternate between negative and positive. So the absolute value of AN is 1 over n squared. Now it turns out that the series 1 over n squared converges using the p-series test with p equals 2, if you're familiar with that test. So the original series converges as well. One caution, however: if the series of absolute values diverges, then the original series may or may not converge. To illustrate this point, let AN be negative 1 to the n times 1 over n. Then the absolute value of AN is 1 over n. And it turns out, again using the p-series test, that the sum of 1 over n diverges, but the original series converges using the alternating series test. So this is an example of a series whose absolute values form a series that diverges, but the original series converges. So we come to one of our main definitions, that of absolute convergence. In light of the fact that if the series of absolute values converges, then the original series converges, in this case, we say that the series converges absolutely, or that the series is absolutely convergent. And I'll abbreviate this with AC. Example 1 was an example of an absolutely convergent series. On the other hand, we saw that if the series of absolute values diverges, then the original series may or may not converge. If a series converges, but the series of absolute values diverges, then we say that the series converges conditionally, or that the series is conditionally convergent, which I'll abbreviate with CC. Example 2 was an example of a conditionally convergent series, since the series converges, but the series of absolute values diverges. So to sum up what we have seen so far, note that every series AN is either absolutely convergent, conditionally convergent, or divergent. It's going to turn out that for most of the series that are typically studied in Calculus 2, a series is either absolutely convergent or it's divergent. Conditional convergence is a rather special type of convergence. So the next thing we're going to do is to investigate some cases where we can easily rule out conditional convergence. If the terms of a series are all greater than or equal to 0, then absolute values won't do anything. So that will mean that the series of absolute values will be the same as the original series. And therefore, both series will either converge or they will both diverge. So conditional convergence is not possible. As an example, let AN be 1 over 2 to the n. These terms are all positive, so the absolute value of AN is still 1 over 2 to the n. It turns out that this series converges by the geometric series test with r equals 1/2. So the series converges absolutely. Another case where conditional convergence is not possible is if the terms are all negative or 0. Then the absolute value of AN will be the opposite of AN for all n. So the sum of AN will be the opposite of the sum of the absolute value of AN. So again, either both series will converge or both will diverge, and conditional convergence is not possible. Convergence or divergence is really a limiting idea that is decided by the tail of a series from some point on. So if there is a number m for which all the terms are positive for n greater than or equal to m, for the tail of the series, the absolute value of AN is the same as AN, so these sums are either both finite or both infinite, since they're the same sum, and before m, we have just finitely many terms, so of course this sum is finite, no matter what. So again, conditional convergence is not possible. Likewise, if there is a number m such that all of the terms are negative from that point on, then the convergence won't be affected by absolute values. Because if the sum of the absolute values starting from m is finite, then the sum starting from m of the original terms will also be finite. And likewise, if one of the series diverges, then so does the other. And there are only finitely many terms before the m, so again, that sum is finite as well. We either have finite plus finite, which is finite, in which case our series is absolutely convergent, or we have finite plus infinite, which is infinite, in which case the series diverges. In summary, if the series of absolute values of AN converges, then the original series converges. In this case, the series AN is called absolutely convergent, or AC. If a series AN converges, but the series of its absolute values diverges, then the series is called conditionally convergent, or CC. Every series is either absolutely convergent, conditionally convergent, or divergent if there's a number m such that the terms are all positive for n greater than or equal to m, or the terms are all negative for n greater than or equal to m, then the series AN is either absolutely convergent or divergent. Conditional convergence in these cases is not possible. I hope you found this video helpful.